Measuring human performance objectively is difficult. We all carry internal biases, and trying to focus our judgment on our own work or the work of our peers often leaves us with a distorted picture. This problem became unavoidable for the European higher education area during the Bologna process. Universities were mandated to shift away from strict memorization and move toward competency-based learning, and that required a massive increase in student autonomy. You cannot build a competency-based model by simply lecturing at people. Students have to develop self-regulation. They need metacognitive awareness, the ability to accurately monitor and direct their own learning process. The most effective way to build that awareness is to transfer the power of evaluation from the teacher directly to the student, specifically through peer review and self-assessment. But historically, this creates a roadblock. Students are notoriously uncalibrated. They systematically overestimate their own abilities, and they struggle to accurately judge the work of their classmates. We want students to govern their own learning, but we can't just hand them the grading pen and hope for the best. To solve the calibration problem, they need an external framework. In 2014, researchers Manuela Raposo Rivas and Esteo Martinez Figueroa set out to test exactly how to build that framework. They designed a quasi-experimental study, tracking 71 first-year preschool education majors. Over the course of a semester, these students completed 4 complex monographic assignments. The cohort was split. 6 control groups evaluated their work using broad, general grading guidelines. The 7 experimental groups were given something far more precise: electronic rubrics, or e-rubrics, defining the exact criteria for success. In this context, a rubric acts as a cognitive scaffold. It provides an explicit external structure of indicators and weights that supports the student's internal judgment. The study aimed to determine if these digital rubrics could force a convergence between student perception and expert judgment, effectively training the novice to see the work through the teacher's eyes. Before looking at how the students judged themselves, we need to look at how they actually performed. This chart displays the overall accumulated scores across all 4 activities for the 13 different groups. The black bars represent the control groups, and the gray bars represent the experimental groups using the e-rubrics. There is a distinct performance ceiling visible here. The experimental groups, operating with transparent criteria, consistently cluster much higher up the y-axis. Looking at the extreme ends of the data makes the divide even clearer. 3 of the experimental groups achieved a perfect 10-point score. 0 control groups managed to reach that mark, and their lowest scores fell well below the experimental minimums. Giving students a detailed map of exactly what is expected of them removes the guesswork from the assignment. Making the evaluative criteria transparent directly elevates their baseline performance. While higher scores are a clear indicator of success, the study's deeper value lies in the longitudinal data, which tracks how student judgment evolved over 4 distinct activities. This animated timeline tracks 3 specific metrics: the teacher's evaluation, the student's self-evaluation, and the peer evaluation. When we isolate the data for Activity 1, we see a massive disconnect. The 3 agents are not aligned at all. Look at the anomalies here. The student's self-evaluation starts artificially high, soaring well above the teacher's baseline. Meanwhile, the peer evaluation is exceptionally harsh, dropping below both the teacher's score and their own self-assessment. This data suggests a lack of calibration. While students start with an optimistic view of their own work, they take a significantly more critical stance toward their classmates, a trend the researchers attribute to a desire to project a heightened sense of evaluative responsibility. Moving into Activity 2, the data takes a sharp turn. This is the reality check phase. The self-evaluation scores plummet. After experiencing the rigorous feedback of the first assignment, the students realize the actual depth of the rubric's criteria. Stripped of their initial overconfidence, they overcorrect. This drop isn't a failure. It is a hallmark of developing metacognitive accuracy. They are finally beginning to understand what they do not know. Looking at the individual graphs for the final 2 phases of the study, Activities 3 and 4, the picture completely changes. The vertical delta between the teacher, self, and peer evaluations virtually disappears. The lines pull tightly together. This physical convergence in the data proves that the cognitive scaffolding worked. Through repeated exposure, the students have internalized the teacher's expert criteria. They are no longer guessing or reacting emotionally. Their internal judgment now mirrors the external rubric. By the end of the semester, the rubric successfully bridged the gap between novice bias and expert assessment. The numerical data proves the accuracy of the method, but the subjective experience of the students dictates whether it can actually be deployed in a real classroom. The response was overwhelmingly positive. 77% of the students approved of the e-rubric model. They reported it made the evaluation process more objective, fairer, and more reflective than traditional grading. When evaluating the specific competency of teamwork, students noted that the rubric allowed them to clearly see who was contributing. As one student put it, the process allowed them to really see what teamwork is. Beyond simple grading, the rubrics facilitated active co-evaluation. The students were actively learning from and with each other. It is easy to look at rubrics merely as administrative tools, a way for faculty to save time or standardize their grading sheets. But the data from the University of Vigo suggests something much more valuable. A properly implemented rubric is a continuous feedback mechanism. It is a learning engine. It serves as the central hub, connecting the teacher, the student, and the peer in an ongoing, synchronized evaluative dialogue. To foster true self-regulated learning, we must treat the ability to measure performance as a core competency, one that requires the same rigorous tools and